When this video is released, Artemis 1 will have been recently launched. This will mark the return of a human presence on the moon, having been 50 years since the last Apollo landing in 1972. Just 3 years before that, in 1969, humans first landed on the moon. Although we can talk so casually about it now, it would have never been possible if not for the invention of the modern rocket. The explosive power of rockets comes from the combustion of an onboard fuel and oxidizer mix, which releases a massive amount of energy in a short amount of time. So much energy that we are able to leave the Earth and reach space. It is a powerful yet admittedly dangerous tool for reaching the heavens. But first, where did it all start? What was the genesis of the rockets that brought us to the moon? Before we answer that question, let's first talk about the most important figure when it comes to making the moon landings possible, Wernher von Braun. Von Braun was one of the most important rocket developers and champions of space exploration in the 20th century. Even from a young age, he was inspired by science fiction, which gave him a profound interest in rocketry and spaceflight. Eventually, in the 1930s, he came to work for the German army to develop liquid-fueled rockets, which would become the aggregate series of missiles. The most well-known of these missiles is the A4, otherwise known as the infamous V2 rocket, used to terrorize cities from afar in World War II. This is the genesis of all space rocket technology, being the first ballistic missile and was the brainchild of von Braun. There is a saying, "War is the mother of invention," which perfectly sums up what became of the V2, a weapon of war, a weapon of destruction, and a weapon of vengeance. Although the V2 was used as a weapon, it was mostly an ineffective one. In its desperation, Germany sought to use the so-called wonder weapons to turn the tide of war in their favor. But these expensive projects only ended up becoming too little, too late. However, the greatest legacy of the V2 and Wernher von Braun is not in its capacity for destruction, but as a blueprint for spaceflight. It was more or less the rocket which launched the space age. The V2 rocket stood at 40 meters high, weighed in at 30,000 kilograms, flew in excess of 5,600 kilometers an hour, and had a range of 320 kilometers away, roughly the straight distance from Paris to London. At launch, the A4 propelled itself for up to 65 seconds on its own power, after which the rocket continued on a ballistic free-fall trajectory, where control would then be taken over by a first-of-its-kind, fully electronic analog computer, taking in input from 2 or 3 gyroscopes, an accelerometer, and radio signals for engine cutoff. In flight, the computer was able to tell when it was during the flight, and then deflect the tail fins and thrust vanes on its own towards its target, or at least close to it. These control vanes would become the precursor to both vernier thrusters and thrust vectoring, common in rockets of later decades. And as for the payload, the V2 was able to carry a 725 kilogram explosive warhead to rain chaos from above. Around 6,000 V2s were made during World War II, and over 3,000 were launched. As for the propellants, for the oxidizer they used liquid oxygen, and the fuel used an ethanol water mix, and were stored in lightweight aluminum magnesium alloy tanks. A strange choice of fuel when compared with modern rockets, and would become the focus of this video. A better choice of fuel available at the time would have been kerosene, but since this was a critically limited resource in Nazi Germany, its supply was very limited and reserved for planes and tanks. kerosene would later return as the fuel of choice for rockets, especially on the Saturn V rocket, which brought humans to the moon. Ethanol, on the other hand, could be used as fuel while being readily available and easy to handle.
But wait a second, isn't ethanol an alcohol?
Yes, it is. Many of you would immediately think about the alcohol we use to avoid the spread of bacteria, like for washing hands. And some of you might also think of alcohol you drink to have a good time. And yes, that is the same alcohol which powered the first missiles. Fun fact, there were even multiple instances of soldiers and technicians of the V2 siphoning the ethanol and drinking it as an alcoholic.
Okay, but you also said that the fuel was a mixture of ethanol and water. But water doesn't burn. So what gives?
Well, the fuel is composed of 75% ethanol and 25% water. And the reason why the water is there is to help lower the temperatures that the combustion process will have to deal with so that the rocket doesn't melt itself in flight. Basically, the water is mostly used as a coolant, and we'll elaborate more on this in the next section.
What about liquid oxygen? Why not just use pressurized gas?
When you liquefy oxygen, it becomes much denser in lesser volumes compared to its gaseous state. You have to remember that normal air is not 100% oxygen, it's just about 20% of it. Even if you make a 100% pressurized oxygen tank, you get much fewer oxygen molecules for the reaction, meaning you get a weaker combustion compared to using liquefied oxygen. Other advantages include a much hotter and faster burn, which is important for the explosive reaction that a rapidly ascending rocket needs. Although sources vary, there are some that report that the internal tanks of the V2 held around 4,200 kilograms of ethyl alcohol and 5,500 kilograms of oxygen to power it. Other sources also state that it has 3,810 kilograms of fuel and 4,910 kilograms of liquid oxygen. As for which of these sources is the real value remains a mystery. Now, let's talk about the single most important part of this rocket and its beating heart, the rocket engine. Where do we even begin with this marvel of engineering? First off, the fuel and oxidizer were fed into the engine at high pressures by pumps driven by steam turbines, which was produced by concentrated hydrogen peroxide and a sodium permanganate catalyst. The turbopump rotates at 4,000 RPM and forces both the fuel and oxidizer out of their tanks at 125 liters per second and will arrive in the combustion chamber at a pressure of 1.5 megapascals. While the liquid oxygen is fed directly into the combustion chamber, the ethanol-water-fuel mixture is first fed throughout the walls of the nozzle, the combustion chamber, and finally into the 18 burners of the LOX mixing and combustion.
We mentioned earlier that the fuel's 25% water was used as a coolant, and this is fully displayed here. As the fuel cools the engine, the water absorbs most of the heat so that the engine is able to keep burning at a manageable temperature. Ultimately, the water reduced the flame temperature, acted as a coolant by turning to steam, augmented the thrust, reduced overall thermal stress, and tended to produce a smoother burn. This process is called regenerative cooling and would become a hallmark of rocket engine design to this day. Before the fuel and oxidizer arrives at the combustion chamber, these are fed into 18 burners, also known as injectors, and are ignited by a spinning electrical igniter at a fuel to oxygen ratio of 0.85 to 1. The chamber's innovative short and round shape made the engine much more efficient than that of older designs, and the wide opening at the bottom allowed rapidly expanding gases to escape with minimal friction and allowed the combustion product to exit at 2,800 degrees Celsius, producing about 25 tons of thrust at launch, and has a sea level specific impulse of 203 seconds. These design choices would directly influence American and Soviet rockets well into the 20th century and would have a lasting legacy.
However, regenerative cooling using the ethanol water fuel mixture was not enough for the temperatures the inner walls were subjected to, which was around 2,800 degrees Celsius, enough to melt steel. So on top of regenerative cooling, film cooling was also utilized where a thin layer of alcohol was continuously injected and applied in the inner chamber walls and would form a barrier as the engine burned, saving the walls of the engine from melting itself. The engine of the V2 was so ahead of its time that both Americans and Soviets scrambled to acquire the technology after World War II. This beating heart is not just what made the V2 possible, but spaceflight as a whole. Here we have the basic chemical reaction of the fuel and oxidizer, which will turn into the products of carbon dioxide and water. But first, we can simplify the equation by removing the water from the fuel as it does not contribute to the combustion. We can then balance the equation, and since we know that this is an explosive reaction, we get this balance equation. Sources differ on the amount of the propellants held by the V2 rocket, but the most common numbers we have found are that 3,810 kilograms of fuel, where 75% is ethanol and 25% is water, and 4,910 kilograms of oxidizer, composed of liquid oxygen. Out of the 3,810 kilograms of fuel, we get 925.5 kilograms of water and 2,875.5 kilograms of ethanol. Dividing the masses of ethanol to LOX, we get an actual fuel to oxygen ratio of 0.582, assuming that all propellants are completely reactant.
However, there is a discrepancy as some sources state that the fuel to oxygen ratio is 0.85 to 1 or even 0.6994 to 1. So which of these two is the real ratio?
Well, you have to remember that there will be real-world inefficiencies that the engine will have to deal with, which is the reality of thermodynamics. Not all of the propellants can be pumped out of the tanks, and during combustion, some molecules eventually end up not mixing and thus won't contribute to the reaction. You also have to remember that the pumps will also produce lower pressures as it uses up its own reactants, meaning less of the propellants are pumped into the chamber over time. Moreover, we have to remember that the propellants would also have impurities, especially the fuel, where 25% is water, in the form of either liquid water or a steam, which would inevitably affect the combustion reaction. All in all, this simple equation for the chemical reaction in the engine is what powers the beating heart of the V2, and it's what literally takes it off the ground and up into the skies. According to the website v2rocket.com, this was how the launch sequence was carried out, and I quote, "The firing troops then would install the electrical igniter into the combustion chamber. After all personnel and vehicles were cleared from the launching site, the troop commander would enter the firing control vehicle and would give the order to launch the V2. The liquid, oxygen, and alcohol then flowed by gravity to the exhaust nozzle, where they were lit by the igniter, which resembled a pinwheel, sparking as it rotated. This 8-ton burning in itself was not sufficient to launch the rocket, but it did give the control officer a visual indication that the rocket was burning properly. Once the launch control officer believed the rocket was ready to fire, an electric command was sent to start the fuel pumps. The fuel pump steam turbine reached full speed, the fuel flow reached its full value of 275 pounds per second, and the engine thrust reached about 69,000 pounds. After the rocket was away, the firing crews would swiftly depart the area." End quote. The V2 would have an extensive legacy, and it would be an understatement to say that it is the grandfather of all rockets and missiles. After World War II, the Americans and Soviets would take this research to develop their space program. The Soviets would produce their own V2s and create new designs from it, creating a long line of rockets that lasts to this day, where the venerable Soyuz rocket traces its roots all the way back to the V2. On the American side, the Mercury series of rockets are directly descended from the V2, and the knowledge of Wernher von Braun would be instrumental in creating the Saturn V, the rocket which brought humans to the moon. It has been 70 years since World War II, at the dawn of the Artemis program, which stands upon the shoulders of giants. Now, more than ever, the V in V2 once stood for vengeance, but now stands for victory towards the stars. That's all. Thank you. Always remember, our sources and references are in the description. You can check it out if you want. That's all.